Hello students, welcome back. In today's class we will be discussing about explanation of electromagnetic induction in terms of Lorentz force. That will also be the proof of Faraday's law. Now, from the previous Faraday's experiment, we have understood that whenever there is a change in magnetic flux passing through a closed circuit, an electric current is induced in the circuit. It can be explained on the basis of Lorentz force. Now in this diagram over here, there is a uniform magnetic field. All this cross over here represents uniform magnetic field which is directed towards the plane of the paper. So this cross is B, which is directed downward. There is a rod JK, okay, conducting rod JK. Suppose the conducting rod JK is being moved without friction on the arm of a U-shaped stationary conductor. So there is a U-shaped stationary conductor, that is MNOL. This is a U-shaped stationary conductor, and suppose this JK is moved in this arm without friction, so frictional force is avoided. The conductor is situated in the magnetic field perpendicular to the plane of a paper directed downward. So the conductor is situated like this, parallel to the plane of the paper, whereas magnetic field is acting downward, that is perpendicular to the plane of the paper. Due to the motion of the conducting rod, the free electron present in the rod are acted upon by a Lorentz force. Now, this rod over here has got this rod has got electrons, and with the velocity, suppose we move this conducting rod towards the right side with velocity v, then the electrons over here will experience a Lorentz force. So the electron over here will experience the Lorentz force, and the force that will also be due to magnetic field will be directed like this. This is the direction of magnetic force Fm, which is equivalent to, or which is equals to Q into V into B. So this Fm, I'll write it over here, is equals to QVB. This is the Lorentz force. We have done the same thing in the previous derivation itself. Now, due to the motion of the conducting rod, the free electron present in the rod are acted upon by a magnetic force of equivalent of magnitude QVB, which takes the electron from the J to the rod to end K. So due to this force over here, the electrons will move towards K and positive charge will be collected over here at J. Since the closed circuit is available to the electron, they drift along the path. Now this electron, okay, electrons, this sign is for, okay, this sign over here, minus sign, is for electron. Electron, because this is a connecting or a closed loop kind of a thing, so the electron will not only move around this rod, it will move from this point K to O. So electrons will move from J to K, from K to O, from O to N, and from N to again back J. So that will be the direction of the flow of electron. Thus an electric current is established. So we know that if electron is moving, electric current will be established, but the direction of the current will be the direction opposite to that of the electron. Okay, that is the rule. So the direction of this electron is this from J to K, whereas the direction of current will be from I will move from K to J. So like this, from J to N. This is the direction of current or I. So current will move in this particular path. So current, the direction of the current will be from J to N, to move to O to K. Okay, so this is the direction of current. So current will flow anti-clockwise and electrons will move clockwise. So along the the rod JK is kept moving in the magnetic field, the electric current continues to flow in the circuit. This current is developed because only of this force Fm. This force Fm is developed because of the magnetic field and the velocity. That means until and unless we keep this conductor moving across this U-shaped rod, then till then only the current will keep on being produced, which is due to the change of magnetic flux. So to change the magnetic flux, this rod has to keep on moving from one point to another in this U-shaped rod. It also means that an EMF is induced in the moving rod, which maintains the current in the circuit. So current is generated. If you have a battery, then only the current will be generated. What does a battery give? Battery provides EMF. So this circuit also provides EMF. This rod provides EMF, due to which the current is being generated. And this EMF or the current or the EMF is known as induced EMF. Since this EMF induced in the rod is due to the motion of the rod, it is also called as motional EMF. So this EMF generated over here is not because of any battery or something, it is because of the motion of this rod JK from one point to another point in this right direction with velocity v. So that EMF will be known as motional EMF. We have also derived the value of motional EMF, which was BVL. In the previous derivation, we have done that. It was BVL. Now, it is due to the Lorentz force acting on the free electrons in the moving rod, okay, due to which the EMF is generated and current is being generated. Suppose the induced EMF in the moving rod JK is E and induced current in the circuit is I. So EMF is denoted by E, current is denoted by I. Okay, current is denoted by I. We know that when a current carrying conductor is in a magnetic field, it is acted upon by a force in the direction given by the Fleming's left-hand rule. Now, using the Fleming's left-hand rule, this is the direction of the current. Direction of the magnetic field is downward. So, with this two, using the Fleming's left-hand rule, a force will be developed. A force will be developed, which will be directed. Suppose if current is in this direction, magnetic field is downward, the force will be developed in this particular direction. Okay, force F will be directed in this particular direction, and the magnitude of the force developed due to the magnetic field will be force developed will be is equals to I L B. Okay, I is the current, L is the length of the conductor, B is the magnetic field. Okay, this is the magnitude of force imposed by the magnetic field. So what are we doing? Okay, I'll explain you again. What are we doing is we are making this rod move towards the right. With that motion, electrons are being drifted from J to K due to Lorentz force, that is Fm. And when this happens, when a conductor moves in a circuit or in the presence of a magnetic field, a Fleming's right-hand rule has to be applied to find the direction of the force, which is directed opposite to that of the motion of the rod. Now, to let this rod keep on moving, to make this keep on moving, what has to be done is we have to apply some force. That means some work has to be done against this force to make the rod moving in the right direction. Okay, the force is in left direction, so there has to be an extra force applied to make this rod move towards the right. For that, some force or some work has to be done. Okay, so to counterbalance this force has to be applied to make this conductor move in right direction. That will be known as force external, which will be opposite to this force. That is why we are putting a negative sign, and the magnitude has to be equal. Okay, so an opposite force has to be applied to make this rod moving in the right direction. So this will be, or I can write minus F, negative of this exact force. So to apply this force, some work has to be done. So when we apply some force to this rod will be displaced by some distance. Okay, it is initially here, so it will be displaced by some distance or displacement del x. So now the rod will be somewhere here. Okay, the rod will be, so this position of the rod is j dash k dash. This displaced by a small displacement del x in the time del t. Okay, the time del t, the rod is being displaced by a small displacement del x. Now to make this move from this point to this point, some work has to be done. So the work done will be is equals to the external force applied into displacement. Force into displacement is work done. So force, external force is minus ILB into displacement is del x. Next, or I can simply write this as W is equals to minus ILB del x. This is the work done in making this conductor move from this point to this point. But we also know that, okay, now we'll continue. W is work done, which is equals to minus ILB del x. Del x is displacement. Okay, displacement or distance. Distance is equals to speed. We'll just use this concept. Distance is equal to speed into time. Speed in this case will be velocity, that is v, into time is del t. So in place of v, in place of del x, we will write v del t. So work done over here will be minus ILB v del t. Now again, what we know is I into del t, or I into t, current into time, is equals to charge. Okay, current into time is charge. So in place of I del t, we will write q. So this becomes minus b v l q. Okay, so your work done is minus b v l q. This work provides the necessary energy for the flow of charge in the circuit. We know that the energy supplied by the cell in flowing unit charge through a circuit is called EMF of the cell. Hence the induced EMF in the rod JK. Okay, now you have to find EMF from the concept that is, potential is equals to work done upon charge. In place of potential difference, we will write EMF. EMF and potential difference is the same. EMF provides potential difference. So in place of E, V, we are writing E. EMF is equals to work done per charge. We are finding the EMF generated while moving the rod from the point JK to point J dash K dash. So EMF is W divided by Q. So in place of W, we'll write this minus B V L Q divided by Q. Q gets cancelled. So your EMF is equals to minus BVL. In the time interval del t, the area of the circuit changes from, okay, initially the area, okay, let me move back to the diagram over here. Initially the area of the circuit, okay, initially the area of the circuit enclosed by this square, by this rod and this U-shaped semiconductor was, initially the area was, okay, I'll write it over here. Initially the area was JNOKJ and it changed to J dash NOK dash J dash. So initially this was the area. After displacing it, this is the new area. So now change in flux. We have to find the change in flux. So the change in flux, okay, I have just written over here the initial area and the final area. Okay, the initial area was J-N-O Kj, final is J-N-O K-J. So the flux is, while changing the area, the flux changes. So the flux phi b, the change in flux will be magnitude of the magnetic field into the change in area, the amount of area which is changing. So the amount of area which is changing, okay, back to the diagram, is area. This small area is changing, this small area is being increased. So this area is length is L, the length of this rod is L. Okay, the length of the rod is L, the area changing is length into breadth, L into del x. So the area changing is L into del x. So this is the amount of change in the flux. Now the rate of change of flux. The rate of change of flux means, how do we write the rate of change of flux? Flux changes with time del t is equals to, using the value of flux from your BL del x by del t. Now next, del x by del t. This is displacement per time. Displacement by time is velocity. So change of flux per time is equals to BL. This is velocity, BL V. This is equation number 2. Initially, this is equation number 1. Now comparing equation 1 and 2. When we compare the equation 1 and 2, we can write is E is equals to minus del phi b by del t. Okay, or when limit del t tends to 0, this can be changed by d phi b by dt. I hope this is similar. This is quite familiar to you people. This is the Faraday's law of electromagnetic induction. This is what we have derived. This is what you have derived for this derivation. That is, derivations of, or the proof of Faraday's law is up to here only. Okay, this is up to for the proof of Faraday's law. The negative sign over here signifies Lenz's law. That is the direction of the current in the circuit due to the induced EMF. Okay, direction of the current and induced EMF is such that the force imposed on the rod opposes the motion of the rod. So this negative sign implies the Lenz's law, and up to here is the derivation of proof of Faraday's law. Now to find the power. Our ultimate thing is to find the power required for pushing the rod from one point to another. The power required to push the rod from one point to another, what we do is, first of all, we find the amount of current. Current is equals to potential difference divided by resistance, E divided by R. Suppose R is the resistance of the rod. Okay, R is the resistance of this rod over here, but resistance of this loop is neglected. Only the resistance of the rod JK is there. So R is the resistance of the rod. E is the EMF which is being generated. So from previously, E which was found out was BLV divided by R. Now the force which was generated, force due to magnetic field. Okay, force on the conductor JK, which is opposite to that of V. We're talking about this force which is opposite to V. So that force was F is equals to ILB. So in place of I, we are writing this value. This becomes BLV divided by R into L into B, which is B into B square L square V divided by R. This is the force. Now ultimately we can find the power. Power is equals to force into velocity. Force is over here, B square L square V divided by R into V. This becomes B square L square V square by R, or can also be written as BLV square by R. This is the power which is required to push the conductor across the U-shaped rod, and some amount of power from this power will also be dissipated as joules heating, and the remaining part is converted into electrical energy. So that power is coming from the work done. Okay? So when we move this rod, some work is done by external agent or external agent to move the rod with uniform velocity v in the magnetic field is mechanical in nature. That mechanical work done, some of the work done will be dissipated in the form of heat, and some will be converted into electrical energy. So this is it for today. Thank you.